So the question that we'll solve today is this one for eigenvalues and eigenvectors, and then I'll just solve the first one, hoping that you guys will be able to solve the second one. Yeah, so practically the aim of this tutorial video is to help you guys understand the concept of eigenvalues, eigenvectors and the like. Then after this video I'll do a 3x3. Okay, right, so let's try to deal with what we have at the moment. So we have this matrix here, which is called matrix A, and matrix A is equal to 4 1 3 2, right? So that's the matrix that we will try to work with. So first thing first, can we get the eigenvalues? So let's get the eigenvalues. So you know that a minus lambda I, the determinant of this should be 0. So we should get the determinant of this and then work around that so that we get the eigenvalues. So our A is 4 1 3 2, and we want to subtract lambda multiplied by an identity matrix 0 1, so 1 0 0 1, and then later on get its determinant, which we should equate to 0. So this will be 4 1 3 2 minus lambda 0 0 lambda, right? So this will be equal to 4 minus lambda 1 3 then 2 minus lambda. We are saying that the determinant of this should be equal to 0, right? So therefore this will be we know that to get the determinant you have to subtract the lower diagonal from the major diagonal. So this therefore will be 3 minus lambda multiplied by 2 minus lambda, this minus 3 times 1, which is just a 3, and this should equal to 0, right? So now we're going to open the brackets. Actually it's supposed to be 4, not 3. So there, supposed to be 4 minus lambda. Okay, yeah, so we open the bracket. So this will be 4 times 2 8, 4 times negative lambda, that will be 4 lambda, negative 4 lambda, and then negative lambda times 2, this will be minus 2 lambda, and then negative lambda multiplied by negative lambda, that will be plus lambda squared minus 3, this should equal to 0. Then from here we're going to collect the like terms together. So this will be lambda squared minus 6 lambda plus 5 is equal to 0. Okay, that is after collecting the like terms together, right? So that we now have this quadratic equation which we should solve, right? So you can solve this using the factorization method. Okay, so let me just try to move this side. Okay, yeah, so we have lambda to the second power minus 6 lambda plus 5. We are saying this should be equal to 0. So therefore we know that this can be, or this should be, lambda squared minus 5 lambda minus lambda plus 5 is equal to 0. Remember, factorization method, we have to look for two numbers where when we multiply those numbers we should get a 5, and then when we add them we should get minus 6. So this would be factorizing out the lambda here. This would be lambda so lambda into lambda squared, there we're going to remain with with a lambda, okay, then minus a 5 here, then over here we are going to have a minus 1, right? So that we've got lambda minus 5 inside the brackets. Then we group these, so this will be lambda minus 1 and also lambda minus 5. Okay, we know anyways that this is actually equal to 0, so we've got two equations. So lambda minus 1 is equal to 0, and then we also have got lambda minus 5 is equal to 0. Therefore the first one will give us lambda is equal to 1, and the second one will give us lambda 2 is equal to 5. So what we've gotten here are the Eigen values, right? So what we have now here are the Eigen values. The next thing is to get the Eigen vector. Okay, so the next thing there is to get the Eigen vector. Now how do we get the Eigen vectors? Okay, so over here, can we now get the Eigen vectors? Can we now get the Eigen vectors? So we know that matrix A minus lambda I multiplied by x, this should be a 0. Okay, so we know that our A is the same matrix 4 1 3 2. So we are saying that let's work with the first lambda. So remember the first lambda is 1, so this will be where there is lambda there, we're going to put a 1. Then we have an identity matrix 0 1, also 1 0 0 1. This multiplied by x1 and x2, we know that should give us 0. Okay, so practically this will be 4 1 3 2 minus, when we we know at the end of the day we still have this. Okay, x1 x2, which should be equal to that. Alright, so 4 minus 1, that is a 3, and then 1 minus 0, a 1, here 3 and a 1 there. So this we are multiplying by x1 and also by x2, which should give us a 0. Okay, right, so from here we can come up with that set of equations, right? So 3 by x1, we are going to have 3x1. In short, we're going to multiply this by that column there. So 3x1 plus x2 is equal to 0. Okay, so since these two are practically linearly dependent, we're just going to get one and work around with that one. Now the way it is, this function here is practically like it will be difficult for us to solve this minus normalizing it, so we'll have to use the normalization problem. In short, we have to normalize this. And how do we normalize this? Is to use this kind of simple equation. Okay, is equal to 1. So I'm trying to simplify this. In short, I'm trying to show you the simplest method of it all, so that the concept can sink. So we are going to work around with this here. In short, we have to normalize this problem. Okay, so we know that we are working around with this equation here, equation 1. So from equation 1 we can make x2 the subject of the formula. So since our equation is this plus x2 is equal to 0, we can make x2 equal to minus 3x1, and then we get this guy here and replace in that function. Okay, so this will be x1 squared plus open brackets, where there's x2 we can put minus 3x1, we square that, and this should be equal to 1, right? So that we have x yeah, so that we've got x1 squared plus 9x1 squared is equal to a 1, right? So 9x1 plus 1 plus x1 squared, practically here we're going to have 10x1 squared, which is equal to 1. Then divide both sides by 10. You cancel that, so I've got x1 squared is equal to 1 over 10. So therefore x1 is just equal to, we can just introduce the roots, okay, so that we can get rid of the square there, and this will just be root of 1 over 10, which is just 1 over root of 10, square root of 10, like that. So this will be x1 is equal to 1 over square root of 10. So we have found x1. How about x2? Remember that we have made x2 the subject there. We've said that x2 is equal to minus 3x1. Therefore, x2 is just minus 3. Where there's x1, we put 1 over square root of 10. So this will be minus 3 over square root of 10 as our x2. Okay. Now from here, we can then come up with a vector which we can call vector 1. Okay, maybe right over here. So this vector called vector 1 will be a function of x1 and x2, and x1 is 1 over square root of 10, and our x2 is minus 3 over square root of 10. So this is our first vector, vector 1, which we've gotten after using the first lambda there. Okay, now from here we can go ahead and get the other vector. Okay, from here we can go ahead and get the other vector using the second Eigen value. And remember that we had this lambda 2 equal to 5, so use the same identity, the same the same logic, that a minus lambda I multiplied by x should give us a 0. So this will be 4, 3, 1, 2, like that, minus, we know that our lambda now is 5, so by now we know that this will be 5, 0, 0, 5. Multiplying this by x1 and x2 is going to give us that 0, 0, right? So this practically will be 4 minus 5, which is going to give us a minus 1, and then 1 here, 3 minus 0, a 3 here, then 2 minus 5 minus 3 there. This we are multiplying by x1 and x2, and that should give us 0. Right, so now from here we can do the multiplication. So it's this row times that column there, so minus x1 plus x2 is equal to 0. If you want, you can also do the second one to be the same thing, because this would be 3x1 minus minus 3x2 is equal to 0. Right, so we can call this equation 1, then we call that equation 2. Okay, yeah, so from here, from equation 1, we can make either x1 or x2 the subject of the formula. Okay, so we are saying that from equation 1, let's use equation 1, which is minus x1 plus x2 is equal to 0. We know that, well, x1 is just going to equal x2. Then we go back to our normalization equation, should be equal to 1. Okay, So we know that where there is x1 we can put x2, or where there is x2 we can put x1. So this will be x1 squared plus, where there is x2 we put x1 squared. This is equal to 1. So 2x1 is equal to 1, or c squared, right? And dividing this by 2, also this side by 2, you cancel that. So you're saying that x1 squared is equal to 1 over 2. So what we can do is to introduce a square root on both sides, so that x1 is just equal to 1 over the square root of 2. So that's our x1. But since you say that x1 is equal to x2, it also means that x2 is also 1 over root of 2. So now we can come up with the second vector. Okay, we can come up with a second vector, which we're going to call vector 2. So vector 2 will be a function of x1 and x2, which is 1 over root of 2, 1 over root of 2, like that. Okay. Then after doing this, right? After doing this, you can go ahead and try to diagonalize. Okay, diagonalize this problem here. Okay, we can go ahead and diagonalize this problem that we have here. Okay, cool. How can we do that? So first thing first with diagonalization. Okay, first thing first with diagonalization, we need to come up with a matrix T, which should be a function of these vectors that we have found. Okay, so I'm saying that with diagonalization. So okay, let me just push this a little bit up like that. So I'm saying that now we are dealing with the diagonalization. Okay, and we're saying that for us to diagonalize, okay, practically with diagonalization, we're just saying that we'll try to convert a normal matrix into a diagonal matrix, right? Okay, yeah, so we're going to come up with a matrix T, which should be a function of the vectors. So vector 1, vector 2 up to vector n. And in our case, we only have two vectors, vector 1 and vector 2. So our T will be vector 1 and also vector 2. In short, our T will be a function of these two vectors. So remember that our vector 1 was 1 over root of 10, and our vector 2 was minus 3 over root of 10. And then our vector 2 was 1 over root of 2, 1 over square root of 2. So we'll work with this particular matrix here. And just a hint there, diagonalization is just a process of converting or transforming a matrix like this one into a diagonal matrix. Now, what is a diagonal matrix? Well, a diagonal matrix is one that takes a form like this one. Let's say we have got numbers here in the main diagonal, and then everywhere else we are going to have zeros. Okay, we're going to have zeros. So such a matrix is what we call a diagonal matrix. So we want to diagonalize this same one here, so that we can come up with a diagonal matrix. Okay, so the biggest question is, how are we going to do this? So now we know that, or if you don't know, to get a diagonal matrix D, okay, so to get a diagonal matrix D, we are going to use this. So it's T inverse multiplied by A and multiply this by the T matrix itself, where A is the original matrix, the T is the one we are just from finding, and then we should also get an inverse of T. So let's first get the inverse. We know that to get the inverse of t, we first have to get the determinant. Okay, so how can we get the determinant? We know that the determinant is just the major diagonal minus the lower diagonal. So our major diagonal is this. So we have to multiply 1 over root of 10 multiplied by 1 over square root of 2 minus, and then the main diagonal, which is minus 3 over root of 10 multiplied by 1 over square root of 2. Right, so this will be 1 times 1 over square root of 10 multiplied by square root of 2. We can multiply what is inside there, and then we keep the square root. So this will be that, the negative plus 3 times 1, 3, divided by square root of 20. Okay, so this will be 1 plus 3, 4 over square root of 20. So we can simplify this by saying 4 over, we can decompose the square root of 20 into square root of 4 and also square root of 5. Okay, so that we have got 4 divided by square root of 2, square root of 4, sorry, is 2, multiplying this by root of 5. So we can now cancel. A number that can go into 4 and 2 is a 2 itself. So we're going to have 2 on top over root of 5. Okay, and this is our determinant there. So that's our determinant of t. But what we want is to get the inverse of t. Okay, what we want is to get the inverse of t. And how can we get the inverse of t? Well, we know that now that we have the determinant, so t inverse, the inverse of t is 1 over the determinant of this multiplied by the adjoint. Okay, multiplying this by the adjoint, and this is going to be 1 over the determinant is 2 divided by root of 5. This will be multiplied by, now remember that our t matrix is this one over here. So to get the adjoint, the major diagonal will swap positions, and then the minor diagonal will be multiplied by -1. Okay, so practically this will be something like this will be something 1 over 2, 1 over root of square root of 2 there, and then this will be positive 3 over root of 10. Okay, and then there will be minus 1 over root of 2, and then over here we're going to have 1 over root of 10. Why? Because we've said that the major diagonal swap positions, and then we're going to multiply the minor diagonal by -1. All right, so at the end of it all, we are going to multiply 1 over determinant times the adjoint, which is 1 over root of 2 there. Okay, so this is going to be, so this is going to be so here we're going to multiply by the, we have that 1 over root of 2, 1 over, so here we're going to have 1 over 1 over square root of 2, here minus 1 over square root of 2, then here we're going to have positive 3 over root of 10. Then over here we are going to have 1 over square root of 10. 1 over square root of 10, like that. Okay, so now our target is to simplify this guy here. That is our target, to simplify this and see if we're going to manage to get a diagonal matrix. Okay, cool. Let's start with the outside there, this 1 over 2 over root of 5. We know that this can be 1 divided by 2 over root of 5, which will just be square root of 5 over 2. In short, we're just getting the inverse of that determinant there. Okay, so our determinant now, so 1 over determinant is now square root of 5 divided by 2. This is being multiplied by what is in the brackets there. Okay, so to reduce the number of steps, okay, what we'll do just, because we know that that term there is just square root of 5 divided by 2, so we've got square root of 5 divided by 2 there. Then now we can multiply to get our inverse of t. So multiplying this by everything in the brackets, this will give us square root of 5 over 2 square root of 2 there, and then over here we're going to have minus square root of 5 divided by 2 root of 2, and then down there we're going to have 3 square root of 5 over 2 root of 10, yeah, and then here we are also going to have square root of 5 divided by 2. So we have this as the t inverse, though we can still simplify this. We can simplify the bottom part there. Okay, so you can simplify this row here at the bottom. How? Well, we know that this can be, so dealing with that part first, we know that the root of 10 there, square root of 10 can be root of 2 multiplied by root of 5. Okay, so this will be square root of 5 divided by 2 root of 2 minus square root of 5 divided by 2 square root of 2 there, and then down there we're going to have 3 square root of 5 divided by 2 square root of 2 square root of 5. Okay, this is supposed to be that, yeah, and then over here we are going to have root of 5 divided by 2 square root of 2 square root of 5, like that, so that we can now cancel. We can cancel some things. Okay, so that and that will go, and that will also go, so that we have this guy here as the simplified inverse of t, square root of 5 over 2 square root of 2 there, and then here we're going to have minus square root of 5 over 2 square root of 2, and then down here we're going to have 3 over 2 square root of 2, and then over here we're going to have 1 over 2 square root of 2. So that is our inverse of t. Okay, so at least we have the inverse of t, which will somewhat make our work a bit easier. Okay, but remember that to diagonalize we need, yeah, so to diagonalize we need, yes, we need the t inverse, but we also need this a multiplied by t. So now the next step is, since we have the inverse, the next step is to get a multiplied by t. So this will be, we know that our a is 4132. Okay, this we are multiplying by t, and remember that our t is 1 over square root of 10, 1 over square root of 2 minus 3 over square root of 10, and also 1 over square root of 2. Now we just have to multiply this. We just have to multiply that. So 4 times that will give us, on top we're going to have a 4 divided by square root of 10, right? Yeah, but we are actually so it's this by that. So 4 times that is giving us 4 over root of 10, but we have to add with 1 times c minus 3 over root of 10 there. remember it's row by column, but so this will be actually be minus now. Why? Because that there is negative. Okay, so it's more like you're saying plus minus 3. You see that, which is just a minus. So minus 3 over root of 10 there. Okay, then again row by column, the same row on top multiplied by the second column here, that one there. So that will be 4 over root of 2, right? And then this one is going to be plus, so plus 1 over square root of 2, like that. Okay, then we do the same with the second row by the columns. Okay, so 3 times 1 over root of 10 is going to be 3 over square root of 10, and then plus minus. Okay, why minus? Because the negative, the 3 there is negative, so positive multiplied by negative is negative, so minus so 2 times minus 3 there, so that will be 6 over square root of 10. And then the last part now, 3 times the other column there, which is just going to be 3 over square root of 2, and then plus 2 times, so 2 times 1 over square root of 2 is just going to be 2 2 over square root of 2. So now what we have here is a times t, which can still be simplified somehow. So can we do that? Yes, we can. Yes, we can, by subtracting and adding. So since the denominators are the same throughout, you can just deal with the numerators and maintain the denominators. So 4 minus 3 there, we're going to have a 1 over square root of 10. Okay, then that part will be 4 plus 1, which is a 5 over square root of 2, right? And then 3 minus 6, that's minus 3 over square root of 10, and then that part there is 3 plus 2, that's a 5. We've got 5 over square root of 10. Alright, so we have this as 8 times t, which is our 8t, right? But for us to diagonalize, remember we have to make sure that, because d is t inverse multiplied by 8t. Okay, so now we have to check this and confirm if this is going to give us a diagonal matrix, which should be have a number here, 0 there, 0, and a particular number there. Let's confirm if this is going to work out. Okay, so yeah, we know that we want to diagonalize this, and this will be, we know this t inverse at, and in this case our t inverse, we have found our t inverse initially to be equal to square root of 5 here over 2 square root of 2, and then minus square root of 5 over 2 root of 2 here, and then down it's actually 3 over square root of 2, and also 1 over, so it's actually 3 here, it's supposed to be 3 over 2 square root of 2, yeah, and then over here it's 1 over 2 square root of 2. That's our t inverse. And then our at, Okay, our AT is actually this matrix here that we just from finding just about now. So we will have to multiply these two. Okay, so multiply this by the other guy, 1 over square root of 10 and 5 over square root of 2, also minus 3 over square root of 10 and 5 over the square root of 2, like that. Then I'm going to multiply using the normal multiplication of matrices, right? So the target is to check if the target here is to get a matrix that should take a form like there should be a number here, you know, a 0 there, a 0 there, and another number there. So that is what we want, is to get a matrix that should take that particular form. Now, can we do the multiplication? So our D will be, so our D will be, we'll be multiplying row by column, right? So this will be, the first part will be square root of 5 divided by 2 root of 10, right? And then plus 3 square root of 5 over 2 root of 10. Okay, then we go to the other column, that one, using the same row, that one. So that will be 5 square root of 5 over 2 square root of 2, right? And then we do the other guy, so this will be minus square root, minus 5 first, then square root of 5 divided by 2 square root of 2 square root of 2. Okay, and then we do the second part row by column again, which will be 3 over 2. Now we know that square root of 2, anyway, yes, the same thing, we are multiplying that by that anyway. I wanted to show the different method, but it's okay. So this will be 2 square root of 2 square root of 10, yeah. Then we're multiplying, we're adding this to the product of those. So this will be minus, why? Because that 3 there is carrying a negative, so minus, this will be 3 over 2 root of 2 root of 10. Then the last part now, the last part now. So 3 by 5, that's a 15 over 2 root of 2 root of 2, right? And then plus 1 times 5, that's a 5 over multiplying the denominator, this will be 2 root of 2 root of 2. Yeah, so this is now when you solve the two part, okay, which is this guy here, okay, when you simplify that, this can be, I'm trying to check if this is going to give us a 1. Okay, let's try to simplify. Okay, so let me push this a bit up. Okay, let's try to simplify that, so that our D is going to be so this will be root of 5 over the second, the denominator there will just be root of 20, like that. And then we're saying this is plus 3 square root of, sorry about that, 3 square root of 5 over 2 root of 20, like that. Then the other guy, this side can also be 5 square root of 5, over 2 square root of 4, then minus 5 square root of 5 over 2 square root of 4. We're just simplifying anyways. Then the bottom part will be, anyway, we know anyway that it's okay. 3 over square root of 20 minus 3 over square root of 20. Then that part will be 15 over 2 square root of 4 plus 5 over 2 square root of 4. So when you reach here, you can see there that this is practically, so when you add this part, you have a 1. Then this is equal to that, so the difference between the two is a 0. Okay, then also that side you get a 0. And then when you add 15 plus 5, that's a 20, divided by 2 root of 4, we know that this is 20 over 4, which is a 5. So here you're going to get a 5. Okay, so this is our diagonal matrix. So this is what we wanted to prove. Okay.